Good morning. Hello and welcome everyone. In today's world where digital ecosystems are expanding faster than ever, security can no longer be a afterthought. It must be engineered, built in, not bolted on. I am thrilled to invite you to a comprehensive 12-part video series on security architecture and engineering, a foundational and advanced exploration that bridges theory, practice, and governance. Whether you are a student beginning your journey, or a cybersecurity practitioner refining your craft, or a compliance professional aligning systems to regulatory mandate, this series has been thoughtfully created for you. In phase 1, we set the groundwork with core concepts. We unpack security models like Bell-LaPadula, Biba, Clark Wilson. We understand system architecture and its principles, including the trusted computing base and the reference monitors. We'll explore preventive, detective, and corrective controls, evaluate systems through common criteria, TCSEC and ITSEC, and dwell into cryptographic design and secure system components like hardware, firmware, and softwares. That's phase 1. In phase 2, we move into deep technical exploration. Here, we explore security design principles like defense in depth, least privilege, and fail secure. You learn about enterprise architecture frameworks such as SAPSA, TOGAF, and ZACMAN. We'll also cover secure coding, SDLC security integration, engineering focused vulnerability management, and dwell into architecture for embedded systems, IoT, mobile, cloud native platforms, and containerization. You will gain insights into hardware based securities like TPMs, HSMs, secure boots, and trust zones, as well as emerging domains like zero trust architecture, confidential computing, and the impact of AI ML on architecture. In phase 3, we'll turn the spotlight to real world relevance through threat modeling methodologies like STRIDE, DREAD, and PASTA. We will analyze actual breaches, what went wrong, and what could have gone right. These case studies will contrast vulnerable versus resilient architectures, giving you blueprints for building secure enterprise patterns while avoiding anti-patterns that exposes organizations to risks. Finally, in phase 4, we will converge technology with governance. We will explore how to map architectural design to standards like ISO 27001 Annex A, NIST SP 800-160, and others. We learn how to perform architecture level risk assessments and how to design systems that are not only secure but compliant with global regulations like GDPR, India's DPDP Act, HIPAA, and PCI DSS. Each episode is crafted with clarity and depth, backed by real world examples, theoretical models, and regulatory insights. My goal is to demystify complex security concepts, empower you to design defensible systems, and help you think like a security architect. So, if you are passionate about building systems that are secure by design, resilient by architecture, and governed by compliance, this series is for you. Please subscribe, follow along, and join me in this transformative journey into security, architecture, and engineering. Let's build a safer digital world, one secure design at a time. This is your host, Savit Vittal Salian. Namaskar. Security, Architecture and Engineering, Part 1. We'll be covering the topics as shown. Security architecture and engineering is the practice of designing and building secure systems and technology environments. It focuses on creating a strong foundation that protects an organization's data, its applications, and infrastructure from threats while ensuring that systems remains reliable and usable. Security architecture engineering practice helps security professionals understand essential principles, models, and practice used in protecting enterprise environments. Security architecture engineering connects deeply with other domains such as asset security, identity and access management, and security operations. In today's complex and interconnected digital world, the importance of security architecture has grown significantly. Organizations rely on well designed security systems to defend against cyber attacks, to meet regulatory requirements, and maintain trust with their customers and partners. This field plays a crucial role in everything from securing the cloud systems and mobile apps to protecting hardware devices and industrial control systems. Security architecture and engineering involves understanding both technical components like encryption, system designs, and network defenses, and human factors like usability and organizational need. It requires a strategic view where security is planned and built into systems from the very beginning rather than added later. What are the components of security design principles? Well, it has least privilege, defense in depth, fail safe defaults, economy of mechanism, complete mediation, open design, separation of duties, least common mechanism, and psychological acceptability. That's the first aspect. The second aspect is trusted computing concept, which involves trusted computing base or TCB, security parameters, security kernel and reference monitor, state machine models, and assurance levels and protection mechanism. For this part 1, we will be looking at in detail on the security design principle aspects. Security design principle. These principles guide how systems should be designed to ensure strong security from the grounds up. Let's start with least privilege. In this, users and systems should only have access they absolutely need, nothing more. Example, theoretical example, if you take it, a junior accountant in a company needs to generate monthly financial reports. Applying the principle of least privilege, their system access should allow them to first view the financial data, generate the report, but they should not allow to modify the company budget or approve transactions or access HR or payroll systems. Hence, they only get access to the tools and the data they need for their job, nothing more. So that's an example from a least privilege perspective, theoretical. If you look at from a real world incident, in the retail data breach case of 2013, attackers gained access to the retailer's network using credentials stolen from a third party HVAC vendor. The HVAC vendor had access to parts of retail network it didn't need for its function, thus violating the principle of least privilege. Now, had retail limited the vendor's access strictly to HVAC related systems and isolated it from sensitive areas like payment and processing, the breach could have been prevented or significantly reduced in scope. But that didn't happen. So that's an example of what happens when you don't apply the least privilege principle, or what could have happened if you had applied, if they had applied, the benefit that you would have gained. Next is defense in depth. Let's look at the same using a theoretical example and a practical. Defense in depth. It's about multi layers of security which are used so that if one layer fails, other still protect the system. So if you look at from a theoretical perspective, example, imagine a company wants to protect its sensitive customer database. It applies multiple layers of security, which includes firewalls to block unauthorized external access. It installs intrusion detection systems to monitor network traffic for suspicious activity. It uses VPN for remote employee access and for encrypting the traffic. It uses multi-factor authentication for all users accessing the internal systems. And it applies access control list to limit which user can see the database. It uses encryption of data at rest and as well as in transit. And it regularly backups the store offline. So they back up regularly and store it offline. They enable logging and monitoring to detect any abnormal access patterns. In this theory, if one layer fails, that the other layers continue to provide protection. So this is a theoretical aspect of defense in depth. An example. Now let's look at a real world case. Let's take the Stuxnet attack. The Stuxnet worm targeted a country's nuclear facility and specifically aimed to sabotage centrifuge control systems. One reason it succeeded was that physical and software defenses were not layered effectively. The systems were air gapped, not connected to the internet, which was one layer. However, USB drives were allowed without proper malware scanning. It's a weakness in second layer or next layer. A proper defense in depth strategy might have included USB port controls or restriction, or whitelisting of executable files, or an endpoint malware detection. If it was there, it could have stopped, or if they had enabled a user behavior analytics in the first place, or if there was an internal segmentation to isolate industrial control system. All of these could have prevented or at least limited the damage caused by Stuxnet. So this is a case where the defense in depth was not in place, not effective enough, and the attack was successful. Had these defense in depth in place, it could have either stopped completely or at least reduced the damage. I hope this example, this two, the theory as well as the actual, helps in understanding the concept of defense in depth. Let's now look at fail-safe defaults. Systems should default to denying access unless it is specifically allowed. It's about denying unless allowed. That's the concept of fail-safe default. Example, theoretical example, if you take a new employee is added to the company's internal systems. By default, they are not granted access to any application or data until their manager assigns the necessary permission. This is an example of fail-safe default, where access is denied by default and only granted explicitly. This minimizes the risk of users having unnecessary or unsafe access. Now let's look at a real world example, say GitHubs. In earlier versions, some platforms would create repositories as public by default unless user remembers to set them as private. Now this led to accidental data exposure where sensitive codes were shared openly. Modern security aware platforms now follow fail-safe defaults. Now repositories, cloud storage bucket and system ports are private or closed by default and must be manually made public. This ensures that unless explicitly allowed, sensitive data is not exposed. So you get permission by default, that's a danger. A fail-safe default feature is you do not get any permission unless explicitly provided by the right authority. It could be your manager, of course. Next is economy of mechanism. Now what's this? Security mechanism should be as simple as possible, making them easier to understand and less likely to have bugs. What does it mean? Let's look at it from an example perspective. Theoretical, let's start with that. A company builds a login system that performs two functions. It checks the username and password and then logs the account if there are 3 failed attempts. The code is short, well documented, easy to review and test. Because it's simple and minimal, there are fewer places for bugs or vulnerability to hide. This is economy of mechanism in action. The idea is the simpler the design, the easier it is to understand, to test and to secure. Now let's look at a real world one. Unix systems use a simple model for the file permission. Either it's read R, write W and execute is X for the owner, group and others. This design has remained largely unchanged for decades. Why? Because it's simple to implement and audit. Users and administrators can easily understand and apply it. The simplicity reduces the chance of misconfiguration. The economy of mechanism here contributes to both usability and security. I hope this gives a better perspective on the concept of economy of mechanism. Let's now look at complete mediation. Every access request should be checked and validated. No shortcuts. Now what does it mean? Let's look at a theoretical example. Imagine a file access system where every time a user tries to open, read or modify a file, the system checks their permission before allowing the access, even if the user accessed the file just a moment ago. This ensures that any change in the user's role or permission or access policy is immediately enforced. Complete mediation means no access is assumed or cached. without rechecking authorization. Let's look at a real world scenario. Some older web application would check a user's login only once. That's at the beginning of the session. Now, if a user permission changed mid-session, for example, they were revoked or demoted, the session would still allow them to perform actions they were no longer authorized for. While modern secure web application revalidates user permission with each sensitive actions like accessing the admin page, changing the setting, or performing transactions. This is an application of complete mediation, ensuring that every access request is checked in real time and not just based on past action. I hope these two examples helps you get a perspective on complete mediation. This sounds very similar to, yes, zero trust. But we have the discussion at the later stages. Let's move to the next topic. Open design. The design should not rely on secrecy to be secure. Security should come from a strong design and controls. What does it mean? Well, again, let's look at from an example perspective, a theoretical to start with. A company designs an encryption system and publishes the algorithm used, allowing security experts to review and test it for any weaknesses. However, the encryption key remains secret. This is open design. The security of the system does not depend on keeping the design secret. It's only about keeping the key confidential. The idea is, don't rely on security through obscurity. Trust comes from transparency and proven design, not hidden codes. Now, let's understand it from a real world example. Let's take AES encryption standards. The advanced encryption standard is one of the most widely used encryption algorithm in the world. Its design and implementation details are publicly available and have been extensively reviewed by the global cryptographic community. Now, despite being openly published, AES remains secure because its strengths come from its mathematical foundation. The keys used in encryption are kept secret, but not the algorithm in itself. This openness builds trust, encourages rigorous testing, and aligns with the open design principle. I hope this helps bring in clarity on what open design is. Next, separation of duties. No single person should have all the controls. Responsibility should be split to prevent abuse or errors. Let's try to understand it from two examples, one theoretical, one real world. Starting with the theory. In a company's financial system, one employee creates vendor payment request. A different employee reviews and approves those payments. And a third employee executes the payment transaction in itself. Here, no single person can both create or approve a transaction. This prevents fraud and reduces errors. This is a textbook application of separation of duties where responsibilities are divided among multiple people to prevent misuse or mistakes. Let's now look at real world data center operation. Now, in a secure data center, a system administrator may be allowed to configure a server, but a security administrator would manage the access control and logs, and an auditor would periodically review all changes and access patterns. This ensures that no single person can make unauthorized change or hide their action and avoid detection. Such separation is commonly enforced in highly regulated environments like banking and government IT systems. I hope this helps with a better perspective on separation of duties. Next, least common mechanism. Minimize shared resources to reduce the risk of one process affecting the others. Well, let's take an example to understand this little better. In a multi-user system, two users run different applications. If both applications write to the same temporary log files, there is a risk that one user could read or interface with the other's data or interfere with the other's data. Instead, each user should have a separate log file in their own private directory. This reduces the chance of data leakage or unintended interference. This is least common mechanism about avoiding sharing system components like file, memory, or communication paths among users unless absolutely necessary. This is to minimize any risk. Now let's look at the same from a real world example. Let's look at the cloud multi-tenancy aspect. Now in a cloud computing, multiple customers or tenants share the same physical infrastructure. If tenants share a common hypervisor, any vulnerability in the hypervisor could allow one tenant to access another tenant's data. But cloud providers apply least common mechanism by using dedicated virtual machines or containers. They isolate customers' workloads. They restrict shared resources where possible, thus minimizing the shared mechanism. It helps the cloud provider reduce cross-tenant risk. This is least common mechanism at play. I hope this helped in some way to better understand this concept. Next is psychological acceptability. Security should not be so hard to use that people try to bypass it. Good security is user friendly. Let's understand this from an example. Theoretically, we take it first. Now, a company implements a multi-factor authentication for employee logins. Instead of using a complicated, slow method like a hardware token with long numeric code, they use a mobile app that provides push notification for approval. Employees find it easy and fast to use, so they comply with the policy without trying to bypass it. This is psychological acceptability. Security mechanism must be easy to understand and use, or users may avoid it or find a way around it or circumvent it. Let's now understand it from a real world case. The Apple Face ID example. Apple Face ID is a security feature that uses facial recognition to unlock your iPhones. It provides strong security, but it is also fast and seamless for the user. It works in the background, requiring almost no action. User accept and consistently use it because it doesn't feel like a burden, making it a great example of psychological acceptability in real world security design. I hope this helps you with a perspective on what psychological ability is all about. We covered all the aspects of the security design principle that we looked at earlier. We will pause here. We covered the original agenda that we thought about, and we'll end the series here. In the next part, we will take the aspect of trusted computing concept. I hope this part has been useful for you on building on the concepts. Let's end the session here. This is your host, Savit Vittal Salian, thanking for the time that you have invested. Much appreciated. See you in part 2. Namaskar.